Oh, didn't see you there. Hey, today we're gonna be looking at string matching algorithms, and I think that string algorithms are really important because there are just too many approaches that you can choose from, and you should be familiar with all of them. We'll look at one of the problems often asked by Google, Citadel, and Oracle, and as simple as it can seem, it's really important to know the string algorithms to get the most optimal solution. So here we go, KMP algorithm for string matching. So the problem we're looking at today is implement str function. We need to return the index of the first occurrence of needle in haystack or -1 if needle is not part of haystack. So the example is input haystack equals hello, needle equals to ll, and the output is going to be 2, index 0, 1, 2. So the substring starts at 2. Example number 2, we have input haystack equals AAAA, needle equals BBA. We can clearly see that there's no pattern like that in our main string, so obviously we return -1. Um, Here are some clarifications. What should we return when needle is an empty string? So we would return 0 when needle is an empty string and is consistent to C's str and Java's index of. Okay, so this question is marked as easy. First of all, obvious solution is gonna be big O of, which is gonna be O of m multiplied by n, where m equals length of our substring and n equals the length of our main string. It'd be easy just comparing regular letters, letter by letter. H equals to L, no, move on. E equals to L, no, move on. L equals to L, yes. Second L equals to L, yes. Then we return the first occurrence. That that's a pretty easy solution, but can we do better? Yes, we can. Indeed, there are two main algorithms that can do it in technically O of n time. Um, O of n time. It's the first algorithm is Rabin-Karp algorithm. Personally, I think that for most string questions, implementing Rabin-Karp algorithm has too much overhead. Indeed, it has good runtime and the space complexity is just going to be constant. But it involves using rolling hash and remembering how to implement rolling hash and how to avoid collisions and checking for collisions. I think you're going to be too overwhelmed on an interview to actually be able to do that. So our second choice is KMP algorithm, which has runtime of big O of n plus m, which is n is going to be more than m, so obviously same runtime, and the space complexity is going to be O of m because we would need to compute the pattern substring for our needle. So let's go and look on the theoretical part of KMP. So a lot of people try to explain this algorithm using terms proper prefix and proper suffix, but personally I find it a lot confusing sometimes, so I'm just gonna try to explain the logic behind it. So we're looking at an example right now, which we have our main string here and our substring right here. And the most straightforward algorithm would just go ahead and start comparing letters A to A, B to B, C to C, A to A, B to B. Then we would find mismatch, which is C and D. So the algorithm, the straightforward one, would go back to the second letter, B, and start comparing it to the beginning of our substring. B to A is not equal, then C to A not equal, A to A is finally equal, and it would go forward. But is there a better way to do this? As humans, we can obviously see that this part, ABC, is equal to this part, ABC. So there's obviously no need in going all the way back and trying to compare all of the letters if we already know that this subpattern equals to this substring. How would we utilize it? One of the ways is to find all of the patterns in our substring, store them somewhere, utilize some extra space, and use those indexes when we're searching. So that's just a small insight in how KMP algorithm works. And now we're gonna actually go and try to demonstrate it on this example and explain how it works. So we would need 2 pointers at first to find patterns in our substring, I and j. We would need some extra memory. We would use an array to store our indexes. So we compare I to j, a to b, which are not equal. We're going to put -1 for both. Gonna move j, compare a to c is not equal. We would go ahead and put -1 again. Finally, a to a. A is equal to a. So here where the terms suffix and prefix come into play, we can see that a is a prefix and a is also a suffix of our small substring. So we would put an index where our prefix ends. So we compared those, a equals to a. We can go forward, move our I and j now, start comparing b to b. B is equal to b, so we're going to put 1 where our prefix ends. So ab is a prefix, ab is a suffix. We move forward. We have c and d now. So we would go ahead. We obviously see that that's a mismatch. So we look at our previous letter, B, see that there's -1. We would just put -1 because there's no way there's a subpattern that we can use. Okay, -1, we reset our I pointer because there's no way we can utilize other subpatterns, and move our j forward. Start comparing again. Hopefully you got the pattern of what we're doing. So we're comparing a to a, we would put 0, then b to b, c to c, a to a again, b to b again, which is going to be 1, 2, 3, 4. And here's when it gets interesting. We've got another mismatch, which c is not equal to d, obviously. We would go back, look at our b, which b had a prefix before it. We'd go and look, which was 1. We'd go back to b and look at the letter after this b, which would be our c. So finally, we have c equals to this c, which we utilized the prefix that we remembered, and which is AB here and AB here, and compare a letter after this prefix, which is C and C. Those are equal, so we get the index of this C and put it to our extra array, which is 2. Move both pointers A to A equal, we put 3 here in our array. So we're done with that. Right now, having some knowledge about our substring, we can start actually searching for it in our main string. So how do we do that? We're going to have 2 pointers, I and j, start comparing those. A equal to A, B to B, C to C, not interesting. Going to go to mismatch. So our first mismatch is C and D. So the idea is really similar to the one that we've been using to find patterns inside of our substring. We go to D, which we have the index of our prefix that we can use remembered here, which is 1. We go to index 1, B, plus 1, meaning index 2, C, and compare those. So here our suffix AB, and here's our prefix AB. Now we can compare C and C. C and C are equal, can go forward. And A equal, and we just keep going and comparing our characters. B and B, DD, AA, BB, CC, AA. And here's another mismatch. Same logic, we go to our substring, go back to B, which we know that there was a prefix at index 4. We'll go back to index 4 plus 1, which is 5, which is D here. We compare those, D and D are equal. Then we can keep comparing, and we finally reach the end of our substring, meaning that we found our match and we matched our substring and we found the solution for the algorithm. So it's not as complicated as a lot of people think, and I really like this algorithm because when you actually get how it works, it's pretty intuitive. Let's jump to the actual implementation and solving our LeetCode problem. So here's our problem again, and we're gonna try to implement our KMP algorithm. So what's our first step? First step is gonna be to implement the function that calculates the pattern inside our substring, inside our needle. I'm gonna call it build pattern and gonna pass the needle to it. Gonna initialize our pattern array to be all -1 for I in needle. Gonna initialize our pointers, I equals 0, j equal to 1, and while j is less than length of the needle, we'll start comparing. If needle I equals to needle j, we would assign pattern j equals to I and would move both pointers. Otherwise, if j is bigger than 0, we would look at our pattern array and reinitialize our j reinitialize actually our I to be our pattern I minus 1 plus 1, and else we would just move j plus 1. So once we're done initializing our pattern array, we return it. In our main function, first step we need to check if our needle is not an empty string. If length of needle is less than 1, we'll return 0, as it was specified right here in our description for the problem. Then we would initialize our 2 pointers, I equals 0, j equals to 0. Then we would start comparing. Well, I plus length of needle minus j less than equal length of the haystack. That's just a fancy way of saying when to stop, which is I, our position in the haystack, plus the length of our needle, the substring, and minus j, meaning how far are we in our substring. Because once we pass this point, there's no possible matches because we already passed the length of the actual substring. We start checking if haystack I would equal to needle j. We check if j equals to length of the needle minus 1, meaning that we reached the end of our substring and we found the actual match. We will return the beginning position of the match. If it's not, we will just increment both pointers. Elif, we will check if j bigger than 0. If it is, we would reinitialize it, j equals pattern j minus 1 plus 1, and else we would just move I plus equal to 1. If we iterated through the whole string and didn't find anything, we would just return -1. Let's check our code real quick. So one more time, we're building our pattern, initializing our pattern array to -1 for I in needle, then initializing our pointers, checking if j is less than length of the needle. If needle I equals to needle j, we would store the value of I in our pattern array, check if it should be I bigger than 0, meaning that our first pointer is bigger than 0, so we can backtrack it to previous prefix index. Here it looks fine. If I is actually 0, we don't have a way to backtrack it anymore. We would just move j plus 1. We return our pattern. Here we're checking if our needle is more than 1. If it's not, we return 0. 2 pointers, I and j. Then we're checking our initial condition. If we still have a possibility to find a match here, start comparing our characters, haystack I and needle j. If j is the last character in our substring, we know that we found the match, so we return I minus j, which is the index of the beginning of the match. If it's not, we move both pointers. If it's not a match, we check our previous prefix in our pattern. If we don't have a way to check our pattern anymore, we just move I plus 1. Let's run it. a little typo. Okay, it passes our original case. Let's try to submit our solution. Of course, because we didn't call. So our solution works. So you might actually wonder why it's showing to be this slow. That's really important to understand for any of your interviews. None of your interviewers are gonna really ask you to implement the KMP algorithm. And when you get a question like this one, implement str function, which returns the first occurrence of needle and haystack, you need to discuss all of the possibilities how to implement the function, and you need to discuss all of the trade-offs. So what's the trade-off here? First trade-off we can see here is the overhead that we're getting. This function has the best big O runtime, which is O of n plus m, which is linear and considered to be really good. But why does it run so slow in our submissions? The reason for that is that we actually have different function calls, and we're having extra memory used, and possibly for small inputs it'd be just better to use our regular n-squared solution. You don't necessarily need to tell that to your interviewer. Obviously, he's going to be really impressed if you implement KMP algorithm and tell all of the trade-offs. But there are a lot of interviewers that gonna ask you what's the best way to solve this problem, and gonna be just fine with your thought process and realizing that, hey, we can use KMP here, and there's also a popular algorithm, Rabin-Karp. And if you discuss a lot of if you discuss the trade-offs between Rabin-Karp, which can be calculating the rolling hash, coming up with the good hash function, also calculating rolling hash and dealing with the collisions, because KMP is more reliable, not having collisions and outputting the correct answer all the time, whereas Rabin-Karp, it depends on a way you implement it. If you don't implement the check after finding your solution, it might output you a false positive result. So yeah guys, we solved our problem in the most optimal runtime. Please comment down below which questions you would like to see me solve in the future. I'll attach the link to the code in the description. I'll attach some articles about Rabin-Karp and KMP in the description. And please go ahead and follow me on LinkedIn and Twitter. And keep coding. Bye.